Hey everybody, thanks for tuning in. I'm just going to do a few examples off the first worksheet that's on the schedule from section 8.3. So, nice thing about the video is you can pause and speed up, slow down, whatever you got to do, but hopefully you attempted this, or at least you attempt it as you go, instead of just watching it. So, be interactive. Alright, this first one, number 17, we've got a figure that looks like a track. And it's made up of two semicircles and kind of a rectangle in the middle. And it tells us that the perimeter is 200 and we want to find the max area of the rectangular region. So we're going to try to maximize the middle piece. But before I do anything, I need to label my diagram. So there's a few ways to do this. This is the radius. So maybe you want to label it R. I'm going to label it X. And then I'm going to label this Y. And so if we're jumping ahead, if you think about the area that we're trying to maximize, that area according to my diagram, I'm going to erase that real quick, is going to be 2x times y. Again, if you wrote it differently, or maybe you wrote it as 2r times y, or the diameter times y, anyway, depends on how you label it. But the other thing I need to use is this hint. The perimeter is 200. So the perimeter is going to be equal to, 2y, right? Y plus y. And then I need basically the circumference of that circle, because it's two semicircles, but they have the same radius. So the circumference is 2 pi r, but the radius is x. So I believe I set that up correctly. So if I move some stuff around, divide by 2, I'm going to get 100 minus pi x equals y. And that guy can get plugged in here. So I got 2x times y, but y is 100 minus pi x. And it's time to take the derivative, set it equal to 0. So I'll leave it at that. Hopefully that helps. I don't think I made a mistake. Let me double check. 2y. 2 pi x, that's the perimeter around the track. I think I'm good to go. Again, I plan on posting some answers, but hopefully that helped you out. All right, number 26. I think this is one of the harder questions. It says that, what's the largest trapezoid, so that's this, that can fit in a semicircle with radius r? So I have this arbitrary circle. So this distance right here is r. And I want to maximize the area of this blue trapezoid. And if you haven't started doing it yet, I really encourage you to try to use these sample points anytime you're on the coordinate axis. And so let's start to try to set up some equations with this very minimal material. All right, we got the area of a trapezoid is 1/2 the height times b1 plus b2. But in this case, the height is y. So we got 1/2 y. And then the base 1 is highlighted over here. Base 1 is this base, but that's going to be 2r. And base 2 is going to be this guy, but that's going to be 2x. So I kind of have a lot of variables happening. So we only have one equation so far, and usually we have two, almost always. And so the other hint is that this semicircle here, we need to come up with an equation And I do think it's the hardest part. What do we use? The area equation, the circumference equation. Those don't have enough variables, and so we want to use kind of a border equation, an equation of the edge. So again, this circle, the equation of any circle is the x squared plus y squared, again this one's centered at the origin, equals r squared. Again, r is some arbitrary radius. If r was 2, it'd be 2 squared. But the real important thing is I have a connection between x, y, and r. So there's a few ways to do this, but just kind of take it a step further. I could write y squared like this. And then I could take the square root, and it would have a plus minus, but since we're talking about a distance, a height, I really only need the plus. And so now I could rewrite this as 1/2 times r squared minus x squared to the 1/2 times 2r plus 2x. And I am ready to take the derivative. And another thing that might bother you, you might be saying, wait, Mr. Smith, what are you talking about? There's an r in there. There is an r, and it's just some arbitrary r. And so you want to, when you take the derivative, you want to treat r as a constant, because it is some semicircle, and it would be staying a constant. So when it's part of the argument, it'd be along for the ride. But what I'm trying to say is your final answer is going to have r's in it. Your answer is going to be an expression with x's and r's. So just a quick side note. Hopefully this is still recording. Beautiful. If you are taking the derivative of, with respect to x, of 2x, plus r squared, that derivative would be the derivative of the outside, the inside's along for the ride, times the derivative of the inside. But when you take the derivative of r with respect to x, if you're treating it as a constant, again, the derivative of any constant is going to be 0. So think about that. But I do think this is a really tricky question. All right, let's look at one more. Number 31, it says that there is 2 hemispheres on top of a cylinder. And so I tried to draw it out. It kind of looks to me like a pill or some capsule of some type. And so the idea is it gives us a volume of this object that's 12 centimeters cubed. And it wants us to find the R that produces the minimum surface area. So let's set up this, this goal first. So the surface area is going to be what we called the lateral surface area. That's my toilet paper roll, plus the surface area of the sphere. So what's it going to look like? The lateral surface area is that 2 pi r times h. That's circumference times the height. When you cut it and open it up, it kind of forms a rectangle. And then the surface area of a sphere, and again I'm using a whole sphere because you can think of the 2 halves as coming together and forming one. It's pi r squared. The only way I remember that, guys, is fun fact. If you take the volume of a sphere and you take the derivative of it the derivative of the volume formula becomes the surface area for a sphere. So that's kind of fun. So I need to minimize this guy. Whoop. But I have too many variables. I have an R and an H. So that's where the hint comes in. So what is the volume of this pill shape? Well, the volume is going to be the volume of a cylinder. So that would be this guy. And then we have to add in the volume of a sphere. And we know that this volume has to be 12. And so this one's kind of a little bit different. I think it's challenging. I mean, all these are challenging. But what I need to do, if you're thinking ahead, is it'd be really nice if I could write H over here. Whoop! I could write H in terms of R. And you've done this with direct substitution. You did it with a proportion. And now the idea is I'm going to use this, this equation and try to get H by itself. So I can then substitute it in. So if I divide everything, whoop, again, there's more than one way to do this, but I'm going to start by dividing by pi r squared. So I have 12 over pi r squared. And that's going to leave me with H plus 4/3 R. So much pressure being on camera. I think that's good. And then I can say, it's kind of messy, that H is equal to 4, no, not 4, 12 over pi r squared minus 4/3 R. So I believe, and there might be a better way, share it with me, but I believe that that blue box could be punched in here. So I'm going to rewrite it and then I'll let you play with it. So the surface area now is 2 pi r times 12 over pi r squared minus 4/3 r plus 4 pi r squared. And it looks like you could simplify some stuff, but it looks like you're going to have all power rules. And at the very end, you guys know. Take the derivative. And if you're going to take it all the way, you're going to set it equal to 0. All right. Doesn't it feel good to exercise your brain? I hope you guys have a great rest of your day. Thanks for watching. Get outside, get some fresh air, and I'll see you guys soon. So, adios.